today's topic is non-ferrous metals and alloys. So non-ferrous metals, they are a wide range of materials. Okay, each has special properties and have variety of different application areas. So we will get introduced to different non-ferrous metals and their alloys in this chapter and their properties, and we will see where they have been used. And I will not go into how they are manufactured or produced. You can guys read through your book. It's briefly mentioned, but it is not, I will not cover it, so it's not going to be asked in the exam. And shape memory alloys, amorphous alloys, metal foams, and rare earth elements and their applications will also be described in this chapter. So when we say non-ferrous metals, as we said, a wide range of materials, right? Aluminum, copper, magnesium, tungsten, tantalum, molybdenum, all these non-ferrous metals, and they are used in variety of ways, even for a certain part. As we can see here, we are seeing the cross section of a jet engine. We are seeing various components and the non-ferrous alloys that are used in manufacturing this part. As we can see, titanium alloys, nickel alloys, mostly alloys that can withstand high temperatures, and aluminum alloys are being used as parts of a jet engine. So aluminum, copper, magnesium, these are more common metals. Tungsten, tantalum, and molybdenum, these are high temperature alloys. Non-ferrous metals, compared to ferrous metals, they are expensive, but have important properties such as corrosion resistance, high thermal and electrical conductivity, low density, ease of fabrication. And if we see the typical examples for applications, for example aluminum, it's usually used in aircraft bodies. Copper for wire for electrical power cords. Zinc, galvanized sheet metal for car bodies. So galvanized means is a protective coating, okay? And titanium in jet engine turbine blades and biomedical implants. Tantalum in rocket engine components. So the common application for these non-ferrous metals and their alloys. So in this table we just see that approximate cost per unit volume for wrought metals and plastics relative to the cost of carbon steel. Wrought means processed, basically worked on. Okay, it's not cast, but it's worked on, like after rolling, extrusion, etc. So if we see the cost, we are seeing how the gold is expensive relative to, then comes the silver. That's why silver is a good conductor but not used, better conductor than copper, but instead copper is being used. So here, right, because it's cheaper. And there are other alloys, aluminum alloys, and you can see how you can see the comparison here when we compare it to carbon steel, cast iron. The non-ferrous alloys, they are expensive, more expensive than carbon steel and cast iron, and plastics also. So in this table we are seeing different non-ferrous metals and alloys, and then what are the general characteristics of them. So these tables and the next this table is just a summary of what we're gonna learn, okay? So let's look at one by one, okay? So aluminum and aluminum alloys, general properties and uses, general characteristics. So general characteristics, general properties, they have high strength to weight ratios. That's why they are being used in aircrafts. Good resistance to corrosion. Think about aluminum foil and you don't see any corrosion on them, right? And high thermal and electrical conductivities, non-toxicity, and reflectivity, ease of formability, machinability, and they are non-magnetic. And what are the uses? Containers and packaging, architectural, structural applications, transportation, electric applications, computers, tablets, smartphones, consumer durables. As you can see, wide range of applications, right? So aluminum and aluminum alloys can be cast or manufactured by powder metallurgy, and we're gonna later see what these are, right? Manufacturing techniques where one uses just melting and casting and other is just using powders to shape the material. So we're gonna all see those techniques. Can be shaped by rolling, extrusion, drawing, forging. Again, manufacturing techniques we're gonna learn to shape the ingot. Can be machined, formed, and welded with relative ease. And aluminum alloys can be hardened by heat treatment or mechanical processing, such as if we do cold working, right, we can increase the hardness. And some aluminum alloys are hardened by heat treatment, so the ones that are used in aircrafts. Okay, so the limitations here is the costs, limited fatigue and fracture strengths. These are the limitations, but of course people are working on enhancing the fatigue and fracture properties of aluminum alloys. So what we are seeing here in this table, manufacturing characteristics and applications of wrought aluminum alloys. As you can see, there are letters A from A to D. A being excellent, D being poor. And the typical applications are given also, depending on what type of alloy it is. And of course, again, I don't want you guys to memorize anything. It is just the name of the alloy and then how it is, characteristics are, how good their characteristics are, and their typical applications. So 2600 series, these are aluminum alloys widely used for vehicles. They are new alloys. They contain lithium as an alloying element and receiving significant interest now. The alloy 2099, for example, contains up to 3% copper, 2% lithium, along with other elements, and has exceptional corrosion resistance, high strength, and 3% increase in stiffness compared to other aluminum alloys. So 1000 series or 1100 series, these are commercially pure alloy, wrought alloy, aluminum alloys. So it has about 99% of aluminum. 7000 series, for example, alloyed with zinc and precipitation hardened. These are the high strengths of an aluminum alloy. That's why they are being used in aircrafts and other structures. So you can, if you're interested, and this is just a reference for you guys to get information about different types of aluminum alloys. And if you are further interested, you can look at Wikipedia that all these type of numberings and alloys, aluminum alloys, are described, what they represent. But I briefly described to you guys. Again, I won't ask something memorization, but you guys need to understand the general characteristics of these alloys and what type of applications they have. Okay, not memorization, and specific things are not going to be asked. Okay, this is just showing you where we use aluminum in a car construction. There are various components of aluminum. They are made by extrusion, sheet forming, and casting. And you see it has an aluminum body structure. It's a automobile that has aluminum body structure. And we are using aluminum alloys in transportation, cars, as well as I said, aircrafts. So next is magnesium and magnesium alloys. So guys, remember to also watch the videos, very important. I put a lot of videos, video links to you guys about all these alloys, and you can watch those and to get more visual information, right? So make sure you guys, when studying, also check out, after studying, maybe check out all these videos. Okay, so magnesium alloys, and actually these are the lightest engineering metal, is magnesium. Okay, lighter than aluminum. It has good vibration damping characteristics. That means they will be used in places where we want to damp the vibration, basically. Main drawback is high cost. So where is it used? Aircraft and missile components, material handling equipment, portable power tools, ladders, luggage, bicycles, sporting goods, and automotive sector. Okay. So magnesium alloys are available as castings, meaning directly shaped from the molten metal, or as wrought products, right? So for example, extrusion, rolling, that's what I said to you guys, right? So the important thing here is magnesium is a powder or in chip form, like the image, we are seeing images of chip. This is obtained after machining, right? These forms oxidize rapidly and create a fire hazard. So therefore machining them comes with difficulties. Okay, so easy to cast but difficult to form because of this danger. Okay, I mean the bulk form is not creating a fire hazard, but it's like powder in chip form, it creates a fire hazard. So we need to be careful when we are machining and grinding them. All right. So in this table we are seeing properties, typical forms of selected wrought magnesium alloys. So the letters that represents the alloy, they are the letters for basically the main alloying elements. So for example, A is aluminum, Z is zinc, right? Or H is thorium, etc. So the letters, these are representing the elements, main elements in the structure. And the numbers are basically indicate the amount of the two principal alloying element in the structure. And the condition, for example, F means as fabricated, and then H means strain hardened, so etc. So these are, of course, you don't need to memorize again, but I'm just telling you so for your future reference. And in this table also we are given that the strength values and ductilities and typical forms of magnesium we obtain, like extrusion, sheet, and forging. I'm sorry. So when it comes to copper and its alloys, very similar to aluminum. Okay, good corrosion resistance, good conductors of electricity and heat. That's why they are used in electrical and electronic components, springs, coins, plumbing components, heat exchangers, marine hardware, because they have good corrosion resistance basically, and consumer goods. And most common alloys we see for copper, we know for copper, brass, and bronze. And beryllium copper is also famous for its good strength and hardness. Brass, you guys know it is an alloy of copper and zinc. And bronze, it's an alloy of copper and tin, right? Here we are given in the table again the properties, typical applications of wrought copper and brasses. So U and S stands for Unified Numbering System. So C represents copper, and different numbers representing different series, like what are, depending on what the compositions are. These numbers are changing. We are also given basically the typical application for certain copper alloys in the table. Okay, so this, I think, continuation of the table. Okay, so the next is nickel and nickel alloys. These alloys, important, they are magnetic. So whenever magnetic materials are required, together with strength, toughness, and corrosion resistance, these materials are good choice, like in electromagnetic applications. And also, the important thing about nickel alloys, they can preserve their strength and corrosion resistance at high temperatures. Therefore, they are used in high temperature applications like jet engine components, nuclear power plants, rockets, also in food handling, in chemical processing equipment, even the coins, marine applications because it's corrosion resistance, etc. So a variety of different alloys are developed depending on what the composition is, what type of properties are desired from that material. Also, the behavior of nickel alloys in machining, forming, casting, welding, they are modified with the alloying elements, and typical alloying elements in nickel and they are chromium, cobalt, and molybdenum. Okay, so these alloys, they are given by their trade names. So Monel is a nickel copper alloy. Hast alloy is nickel chromium alloy, good corrosion resistance, high strength at elevated temperatures. Nichrome is an alloy of nickel, chromium, and iron, has high electrical resistance, high resistance to oxidation, and used for electrical heating elements. Invar and cover, these are alloys of iron and nickel. They have relatively low sensitivity to temperature changes. And if you remember, we talked about Invar having low thermal expansion coefficient. So here, based on their trade names, also their composition is given, their properties are given, and typical applications are given for nickel alloys. So you can see wide range of applications are available for nickel alloys. Oh, okay, so next is, we did this one. So next one is super alloys. So when we say super alloys, these are important in high temperature applications. That's why they are also called heat resistant and or high temperature alloys. Usually can withstand up to 1200 degrees C. They have good resistance to corrosion, mechanical and thermal fatigue, mechanical and thermal shock, creep and erosion at elevated temperatures. So thermal shock is when we suddenly change the temperature of a material, because inside the material there will be differences of thermal expansion that might create stress in the material, and those stresses can crack the material. Therefore, the thermal shock is the ability of the material to withstand the sudden temperature changes. So superalloys have all these properties. So where do we use those? In jet engines, gas turbines, where there's high temperatures, and reciprocating engines, rocket engines, tools, dies, for hot working operations, nuclear, chemical, and petrochemical industries. So again, the superalloys, they are identified by their trade names and special numbering systems. They come in variety of shapes. They are based on iron, cobalt, or nickel. So there's iron-based superalloys, mainly iron, and so the iron-based ones, they're called Incolloy series. Incolloy series, and as I said, made of iron, like up to 67% of iron, and cobalt-based superalloys. These are not as strong as nickel-based superalloys, but they retain their strength at higher temperatures. And there is nickel-based superalloys, also mainly nickel. And these are the most common superalloys, and they have a variety of composition, variety of different names, such as Inconel. Of course, it a lot of other names. I'm just giving you common ones. Okay, so as you can see, the trade names of different nickel-based superalloys are given here. And the condition, is it cast, is it after cold working road, and what is the strength, yield strength, and what are the ductilities, and where they are used. As you can see, most commonly jet engines and aircraft engines, and for high temperature applications. So titanium and titanium alloys, these are good high strength to weight ratio, but they are unfortunately expensive. They have a good corrosion resistance at both room temperature and elevated temperatures. Pure titanium has actually excellent corrosion resistance, and titanium has different crystal structures, again depending on temperature, composition. It can be BCC or HCP. Of course, this changes the behavior. BCC will be ductile, HCP will be brittle, and of course when it's brittle, it's sensitive to stress corrosion. Where do we use them? In aircraft, jet engines, racing cars, golf clubs, and chemical, petrochemical, and marine components, submarine hulls, armor plate, medical applications like implants that we put into our bodies. And titanium alloys, they can withstand up to surface temperatures of 550 degrees C, and they can preserve their properties at these temperatures for a long period of time. Alloying elements, very important. It can but alloying elements, we can control workability, machinability, strength, and hardenability of the titanium alloys. And usually the alloying elements are aluminum, molybdenum, manganese. So of course depending on the alloying elements and heat treatments, we have different properties that can be obtained from these titanium alloys. And there are intermetallic compounds like aluminides, like titanium aluminide, such as this one, titanium aluminide and titanium aluminide. So these are, remember, compounds, intermetallic, react at certain ratios of the elements. This one has high stiffness, lower density than conventional titanium alloys, and can withstand up to higher temperatures. Again, here we are given different types of titanium alloys, and their compositions are given, their names are given, compositions are given, how it is heat treated, annealed and age hardening, etc. And then we have the temperature they can stand to, and I think those are annealed temperatures. Yeah, annealing temperatures. And then the high strength, the strength volutes, and ductility, and again ductility. These are given. So refractory metals and alloys. What do we call refractory metals? So why refractory? Refractory means these metals have high melting points. Okay, high melting points. So molybdenum, niobium, tungsten, and tantalum, right? These are having high melting points, and they can maintain their strength at very high temperatures, up to 2200 degrees C. Therefore, where they are used in rocket engines, gas turbines, other aerospace application, nuclear power plants, chemical industries, tool and die materials. Okay, so again, what are refractory metals? We said one of them is molybdenum. So, and what is the characteristics of molybdenum here, right? So it has high melting point, high modulus of elasticity, good resistance to thermal shock, good electrical and thermal conductivities. They are being used in rockets, jet engines, honeycomb structures, meaning in composites in the shape of honeycombs. They are used. And electronic components, heating elements, dies for die casting. But the bad thing is here it has a low resistance to oxidation, which can change the properties, right? Because the surface is oxidized, that it can induce undesired properties to the material. Then we have the niobium, and then it has good conductivity, formability, higher corrosion resistance than other refractory metals, again used in rockets, missiles, nuclear, chemical, and superconductor applications. Okay, next is tungsten. And tungsten is the most abundant of all refractory metals and the highest melting point of any other metal in the periodic table. Okay, so the temperatures it can resist up to without melting is 2410 degrees C. So it has also high strength at elevated temperatures, high density, so this is something bad, right? High density, brittle at low temperatures, and poor resistance to oxidation. Again, uses are rockets and jet engines, missiles, welding electrodes, circuit breakers, tooling for electrical discharge machining, spark plug electrodes. So wherever there is this high temperature resistance is required, tungsten is used. If there is a high temperature requirement with a high strength at elevated temperatures, then tungsten is being used. Tungsten, you know, most commonly in light bulbs we are using, right? So tantalum is, again, it has a high melting point, 3000 degrees C, good corrosion resistance, good ductility, high density, again used in missiles, aircraft, electrolytic capacitors, electrical, electronic, medical products, chemical industries, furnaces, acid resistant heat exchangers. So as you can see, all these alloys have unique properties and unique application areas. All have wide range of different properties, property combinations that are making them suitable for different type of specific applications. Okay, so the next topic is beryllium. So when we look at beryllium and its alloys, basically, it has high strength to weight ratio, and unalloyed beryllium is used in rocket engines, space and missile structures, aircraft disc brakes, precision instruments and mirrors, also used in nuclear applications, X-rays application because of its low neutron absorption, and it is also being used as an alloying element, and its alloys of copper and nickel are used in various applications. So the bad thing about this is it is toxic. Okay. So zirconium. And zirconium has a good strength, ductility at elevated temperatures, good corrosion resistance because of the formation of the oxide film on it. The oxide film protects for further corrosion, just like aluminum. It forms aluminum oxide on top. So zirconium is used in electronic components, in nuclear reactors, because of its low neutron absorption. And lithium. Lithium is the lightest metal and widely used in rechargeable batteries. Rechargeable batteries, have application in computers, cell phones, and it can be used to form alloys with aluminum, magnesium for lightweight applications. So what about low melting alloys? As the name implies, these are alloys with low melting temperatures. And the major metals in this category, they are lead, zinc, and tin, and their alloys. So lead, it has the properties of high density, resistance to corrosion, it has low strength, ductility and good formability, toxic, and which limits its use, of course, and it has been used as solid lubricants for hot metal forming operation. Remember, we will need lubricants to reduce the friction between the die and the working part. And applications of lead is piping, collapsible tubing, bearing alloys, cable sheeting, foil, roofing, and lead acid storage batteries, damping vibrations, radiation shielding against X-rays, ammunition, and the chemical industry. So wide range of applications. So basically lead, because it has a low melting point, together with tin, it is mainly used as soldering alloys to make electrical connections. Okay. So I'm sorry, it's not correct. It should be SN. Okay, that's tin, right? Okay, so it has low hardness. So sometimes you see in the books it says soft, right? So it says lead is soft. That means it has low hardness. Okay, so it has low hardness. So these are the general properties for lead. So zinc. Zinc is actually a commonly used metal. We can say it is fourth most utilized after iron, aluminum, and copper. So it has major uses. The first one is it is used for galvanizing iron, steel, sheet, or wire. That means it is acting as a coating. If you guys ever learned corrosion, so galvanizing means iron and zinc forming galvanic couples. So what happens is, instead of, it's a corrosion protection, it's instead of the iron, the zinc corrodes and dissolves into the environment. Okay, so also it is for casting, because it has low melting point, it is preferred for easily castable parts. Okay, so it is used in fuel pumps, grills for automobiles, household appliances, etc. So the major alloying elements in zinc are aluminum, copper, magnesium. They provide strength, more dimensional control during the casting of the metal. Tin has even lower melting point than lead, and it has low strength, low hardness, and good ductility. Most extensive use is as a protective coating on steel, and in making containers like tin cans for food or various other products. So as I said, tin lead alloys, because they are having low melting point, they are used as soldering materials. It has, of course, many applications, one of which is it is used as a lining for water distillation plants. It has also been used as dental alloys, and as we can say, different alloys of tin will have a wide range of composition and different melting points, different properties, and different application areas. So when it comes to precious metals, also called noble metals, these are gold, silver, platinum. Most common applications I see for these precious metals, they are actually antibacterial. If you ever use the burn cream, it will have a silver in it because it will kill bacteria. So when it comes in contact with the bacteria, it damages the bacteria wall. And besides those, of course, they are ductile and they have good corrosion resistance. So gold, for example, it's been used in dental work, electroplating, electrical contacts. So electroplating is like coating a material with gold. And silver, it is also corrosion resistance, and the most important thing about silver, I mentioned it before, it has the highest electrical and thermal conductivity of any metal. Again, used as electroplating solders and bearing linings, food and chemical equipment. Platinum is again ductile and good corrosion resistance. It's been used in electrical contacts, spark plug electrodes, catalysts for automobile pollution control devices. And basically it provides surface for these reactions to take place in filaments and nozzles, in dies for extruding glass fibers, in thermocouple and dental work. So they have many wide range of applications. Of course, these are just covering few of those. These materials are chemically inert, but they are available in limited supply. Of course, they are also used in jewelry. They possess high density. So more advanced alloys, shape memory alloys, also called smart materials. And I suggest you guys again check the videos I sent you, okay? Because there are demonstrations for these materials. So why do we call these smart? Because they can return to their original shape. They can remember their original shape when they deformed. So for example, this is what is the original shape at low temperature. You deform it, and if you heat them up, it will go back to its original shape. Okay, so of course there are application areas can be variety of application areas for that, and this is you generally used to generate motion or force in temperature sensitive actuators. They have good ductility, corrosion resistance, high electrical conductivity, is used for sensors, relays, pumps, switches, connectors, clamps, stents for blocked arteries, because you insert it and it goes back to its original shape, right? Seals, fasteners, wide range of applications. So what is the component of these alloys? So why this phase change actually why this remembrance of the shape happens? It is actually related to phase transformation. So different phases are there inside the composition material, and complex phase transformation is taking place, and that is making the material go back to its original shape. Shape memory alloys, they are 55% nickel, 45% titanium. There are other shape memory alloys like copper, aluminum, nickel, copper, zinc, aluminum, etc. For example, you have a coil, let's say, and you deformed it, and by heating it up, it will go back to its original shape, the coil shape. It's reversible deformation. Okay. So amorphous alloys or metallic glasses. So what does amorphous mean, if you guys remember? Amorphous means there is no wide range of order in the material. Atoms are random arrangement there is in the material. They are not arranged in an order. So these such atomic configuration is usually observed in glasses, right? Glasses have a random arrangement of atoms. That's why they are actually transparent. Because this structure interacts with light this way, gives it a transparent view, because the light enters and goes through the material because of this arrangement, random arrangement of atoms. That's why the glasses are amorphous. That's why amorphous alloys also called metallic glasses. So how can we achieve random orientation of atoms? If we, from a molten state, if we rapidly solidify an alloy, we won't provide the time for atoms to go to their equilibrium positions, thermodynamically equilibrium positions, because we are not giving the time and energy. We are just rapidly cooling. The atoms don't have time to arrange themselves to an oriented positions. Okay, so that's why they are randomly oriented in the structure. And therefore, what type of alloys are these? Usually these are iron, nickel, chromium, alloyed with carbon, phosphorus, boron, aluminum, and silicon. So where do we use these? We use this in golf club heads. Actually, that's not gold. Baseball bats coated with a composite of amorphous metal by thermal spraying. Okay, so excellent corrosion resistance, good ductility, high strength, very low magnetic hysteresis. So let me see if we have a figure. Okay. So what it means is, so when we apply an external magnetic field, ferromagnetic materials such as iron, the atomic dipoles align themselves with it, like align along the magnetic field direction, and when the field is removed, sometimes that alignment still remains. So we say the material has become magnetized, and even if we remove it, once we magnetize it, it will still stay inside the material indefinitely. So when it is low, actually this process is low, that means these materials can be used in magnetic steel cores for transformers, generators, motors, magnetic amplifiers, etc. So it gives us this low magnetic hysteresis loss, provide great efficiency in these applications. But the fabrication costs are high for these materials. So actually amorphous steels have been demonstrated to have strengths twice those of high strength steels. So that's cool. What about metal foams and metamaterials? What are these? So as you can understand, metal foams, those are very porous structures, right? As we see in the image, which is an image of a metal foam in an orthopedic implant that is used for bone growth, because the bone also has a similar structure. Okay, so these only have 5 to 20% of metal. The rest is basically pores, empty space, right? These are usually made for aluminum alloys. So I heard it for aluminum foams, but can be obtained also for titanium and some other metals. But how do we do that? By simply blowing air into a molten metal. So since these are porous structures, they can be used as filters or, as I said, or orthopedic implants. Of course, these structures provide unique combinations of strength to density, stiffness to density ratios. And they are very lightweight, right? And therefore they are attractive for aerospace applications because of the porosity, basically. So think about if we can have this more ordered. You see in the image it is more random, right? The pore structure is random, structure is random. Think about it is like you have a material that this porous structure and construction is very ordered. You have a shaped porous structure in the material. That's when this is called metamaterials. Okay, so if you look at this image, again these metamaterials, they have high porosity, but think about it has a unit cell that is repeated to fill a volume. And these structure, the good thing is about these structure, this type of porous structure, highly organized, they can be done in any way to achieve any type of mechanical, thermal, electrical properties. So they can be arranged in a way to scatter the light differently, okay, to have negative refractory indices. So this can create invisibility, for example. So you can play, because of the way you arrange the structure, you can play with the properties of the materials differently. So rare earth elements. These rare earth elements, they are not called rare because they are rare. It is because they are difficult to mine, difficult to extract from earth. Okay, but they all have unique magnetic, optical, electrical properties, and they are being used in modern technology like portable electronic devices, computer devices, in radiation shielding, in generating radiation, etc. They all have unique application areas. So one is yttrium, that is used in fluorescent lamps, light emitting diodes, laser technology, superconductor applications. Another one is lanthanum. That one is used in catalytic converters, anode materials for batteries. So it is used in batteries mainly. So this prosium, that one is used in lasers, lightning, and in devices where you measure the radiation exposure. Next is neodymium, which is used in creating, together with iron and boron, create strongest permanent magnets known. Actually, such as the ones used where small but powerful magnets are required, such as in ear headphones and microphones. cerium is mainly used in catalytic converters in automobiles. So basically it activates the chemical reactions. And for oxidation of carbon monoxide, it is used in glass manufacturing as permanent magnets, fuel cells, and in polishing optical components. So wide range of applications. Samarium is the second strongest permanent magnet. However, they have better stability and can be used at temperatures up to 700 degrees C. Because neodymium magnets, even they are the strongest, they are limited. They can be used up to 300 degrees C or so. Terbium is used in electronic devices and sensors. It has the highest magnetostriction of any alloy. Remember, magnetostriction is where you try to apply force and the material generates magnetic field, or when you apply magnetic field it generates a force. Okay, so of course there are other rare earth elements. These are the important ones. So of course, in summary, we learned that there are a large variety of non-ferrous metals and alloys. They have a wide range of applications that cannot be provided by the ferrous alloys. Okay, so the most common ones are aluminum, magnesium, copper, and their alloys. Nickel, titanium, refractory alloys, superalloys, they are used for high temperature applications. There are also low melting alloys. These are low melting point alloys and precious metals with unique properties. And there are shape memory alloys, amorphous alloys, metal foams which are lightweight and attractive for aerospace, and rare earth elements which are difficult to mine in large quantities, but they have a wide spread application areas. So in general, you guys, of course, this a lot of information in these chapters, but I want you guys to know if, for example, it says this material is the best conducting material, then know that material, right? I can ask in the question which one of these options giving you the most electrically conductive material, for example, okay? Or so get a general idea of their application areas. Do not memorize specific application areas, but get a general idea of the application areas, properties, and so understand which one is low strength, which materials are high strength. So understand which materials we are using at higher temperatures, which one we are using at low temperatures, and why, and characteristics of each material in general sense. Okay, so that's it. Okay guys, so next chapter will be polymers. Okay.